This talk is going to be given by John Nordby, who's the CTO of Sound Sensing, a company from Oslo, and who specialize in TinyML and audio signals. And looking forward to hearing this talk. John, welcome.
There we go. Thank you so much for the introduction. I'm here to talk about emlearn, scikit-learn for microcontrollers. I'm from Sound Sensing. We provide end-to-end solution for maintaining, that helps to maintain buildings, such as this. For example, we monitor the ventilation system, heating and cooling, using a combination of sound and vibration sensors. And for us, TinyML is a way to be able to put smart algorithms on the sensor themselves in order to extract interesting information about particular machines, and then transport that to the cloud, where we do the continuous learning to estimate machine health and do anomaly detection. I'll talk about emlearn open source project. I'll give a quick introduction, and then we'll talk a bit more specifically about tree-based ensemble models, which are very useful in TinyML settings. Cover some projects which are been made with emlearn. It's now a 6-year-old library, so there has been a lot of usage, even though I never really did any marketing on it until this year. And then we'll talk about building TinyML applications using primarily Python, which I believe can be quite interesting going forward and open for more opportunities for more people. Yes. So in my experience is that TinyML are primarily sensor data analysis solutions where we are running on a small system, and there's many components to this which we hear about at this conference, and then emlearn fits in tools for deploying the model onto the device or standard microcontroller. And there are many benefits which have been covered by many others. So there are tons of applications in all spaces, and I will give 3 concrete examples a bit later in the talk. So there's kind of 2 sides to a TinyML project or solution. There is the training part, which happens on your computer, on a standard machine, primarily in Python. That's like the standard language to go to that basically everyone uses. And it's important then for us to support standard libraries, such as scikit-learn and keras. And then we provide like a one-line function to export this to an optimized C model. And then that can go onto the embedded side, and where it's very important that the code is predominantly C-based, so we provide portable C99 code without any dynamic allocations. It's header only, so it's easy to include. And we have high test coverage, so you can use this in real-world situations and trust it. And we support fixed-point math for some of the models. And it's important, as always, to keep the program size quite small. So we support the most common tasks that are relevant, such as classification, regression, and anomaly detection. Support selection of relevant embedded friendly models, such as decision trees, random forest, KNN, etc. We do have basic support for neural networks, but definitely it's not an area of focus for us, so there are much better tools available for that specifically. Using it is very simple. We do follow like a scikit-learn type philosophy. It's important to keep things simple and easy. You install it with pip, or include it as a Git submodule. You train then using the familiar tools, and probably you have already existing code, so on, for example, using keras or using scikit-learn. And then you use this function to convert it into a optimized C model. You can then save this as a generated header file, and you can include this in your project on your device, and use the predict functions that provides. So this is really all there is to it. You can solve problems in a simple way. So talk about tree-based models, such as random forest, decision trees, extra trees. There are like several ways of optimizing similar models. This is the most popular model in emlearn. It's very relevant for TinyML systems. They really have very fast inference times, often in the microsecond range. They use very little RAM, basically just a feature vector and not much else. And they're also very easy to get good performance out of. You don't need to deal a lot with hyperparameters, pruning, like all these things that come along with neural networks. So, but of course, neural networks are all the rage. So are these models still relevant? And I would argue yes, that they can be in a range of settings. So if you have a task which is relatively low complexity, then really I would recommend you start with something like a random forest. It's very simple. You'll get excellent performance with almost any work. And it can actually be, in this region, it can be quite tricky to get a neural network to match. Not impossible, but it just takes time and fiddling. So that's an obvious area. And in the medium complexity range, this is where you might have some time series that are semi-complex. And it can actually be an alternative to deep learning in some cases if you have reasonable feature engineering. So you're relying on that. For example, Elst et al., they showed on a human activity detection problem that they could get similar predictive performance with the forest-based approach, but at 10 to 100x better inference time. It's also relevant in some high complexity tasks. These are tasks where basically the neural network is the go-to solution. And you need to have it at some point. But you can combine a simpler model, tree-based or even logistic regression sometimes, because many of the classes that your system encounters might be quite simple to discriminate. Especially in continuous monitoring scenarios, 99% of the time there might be essentially nothing going on. And separating that out can be done with a simple model. So like here et al., they showed also an activity detection problem that by first piping it to a simple model and deciding between the easy classes, and then taking the trickier ones, passing that to the neural network, they could save up to 67% energy. So there is a high relevance across the range of tasks for this. It's important still to compress. These are quite simple models, but they can still take a lot of time, space if you don't consider it. So we do leaf deduplication, and this is currently implemented with argmax. So instead of storing the class probabilities in the leaves, so the outcomes of each decision tree, which scikit-learn does, we store just the class index. So this means that we're doing an argmax operation. This is much smaller, saving up to 80% of the space. There is a trade-off in predictive performance, and I'll get to some improvements we're doing there. And we also support two different inference modes. So we have what we call loadable, where we have a data structure that describes the model, and then there's a single function taking that data structure that actually evaluates the tree. This works then for any model. You can load that at runtime, which is nice, but you can also generate code for a specific model. Then you cannot meaningfully load at runtime, but it supports integer precision, and sometimes the compiler can do a better job with optimizing that. So we have seen over the years that actually basically all the tasks that we could have experience with could be done with integer-based feature representation. So we did a control experiment on this on 48 data sets from the OpenML CC18 benchmark suite, and we could confirm that, yeah, indeed, you can. It's basically lossless to go to in 16. So in the next version of emlearn, that will be the standard representation also for this loadable type model, because it really is a pure win. And especially for a device without FPU, you will get much higher inference time and also reduced code size. Back to this leaf, these leaves and storing that. So we did also some recent research on the same data set from this CC18 benchmark, and we set a conservative, like the acceptable drop for a tuned model at 1 percentage point in the green. And we saw that actually 78% of the data sets, if you do the argmax, they fail that threshold. And some have quite a large drop. So we wanted better tools to have to balance this trade-off. And we found that you can use k-means clustering on these class probabilities in the leaves to select a small subset, a small set of data-specific or representative leaf nodes and be able to tune that. And you can, with that, with small as 4 or 8 per class, this is sufficient to basically match the, you get then the performance in that boundary that you want. And in most cases, a majority of the cases, it's a tiny increase in the model size. And in all cases, you, even where you do increase a bit from argmax, you still save a lot compared to not having this kind of compression. So this is, we'll probably write a paper on this, and it will come in a future version. Some projects. This is from a student at Virginia Tech, detecting abnormal behavior in cattle using accelerometer data. So they classify the activities of the cow into these categories, and then you can look at these proportions relative to what is normal, in order to indicate that there might be something abnormal going on. It could be a health issue, or maybe the herd is being threatened by some stressors. And they show that you could do this under 1 milliwatt by doing it on sensor, and which was 50 times lower power than sending raw data, which is of course a huge increase in battery lifetime, or potentially the size of the device. Here's another example from Samsung research. We're estimating the breathing rate using these kind of standard earable in-ear devices. And breathing rate is critical to monitor for people that have respiratory health problems. And monitoring today in everyday use is quite tricky with existing tools outside of the clinical context. So they combine the audio data, so estimate the breathing rate from audio, but also estimate it from the accelerometer, and then merge these two results. They used the random forest classifier with the emlearn for the audio part, and they show that when you do this multimodality, you're able to have a robust solution in everyday use, where sometimes you're talking and the audio doesn't work, sometimes you're moving and the accelerometer doesn't work, but combining this, you can get good results. Here's another example from localizing faults in the electric grid. This is from Sandia Labs in the US. And this is not necessarily a TinyML or typical TinyML solution. It's a bit interesting. So it's when a fault occurs in a power line, you get this ripple through the network. And you can actually detect this at a different location. And because it's how it propagates, its characteristic of where it came from, you can detect which segment the fault originated. So this is not necessarily tiny in terms of battery power and size, but these boards, the DSP boards, the microcontroller boards, are some of the best in terms of the I/O capabilities that you have, which makes it attractive to use also for this kind of cases. And you can build a standalone solution, which can easily be connected into a bigger system, potentially over legacy protocols, etc. So it can also be relevant outside the tiny sphere. Here's a little research project of mine, looking at how cost-constrained are we actually in the TinyML sphere when we're talking about these low to medium complexity tasks. And the question I pose myself, like, can we make a useful TinyML system, so complete system, within $1 bill of materials? And by doing a bunch of research and picking hardware, it's actually possible to do, for example, either motion detection and transmitting over BLE, or sound detection within this bill of material band. But you need to fit in 4 kilobytes of RAM and 32 kilobytes of flash. I got the board recently and I did some tests, and we can see that doing, for example, accelerometer data is quite feasible in this MCU resource constraints. Audio, which I like the most, is a bit more tricky, but we do have a working pipeline for spectrogram feature extraction, and we still have 800 bytes of RAM and 10 kilobytes of flash for the model. So I think we can do simple anomaly detection, simple sound events, and potentially some simple sound commands with this. So this project you can follow on Hackaday if you're interested in this ultra low. It's quite fun to play within these constraints. So over to Python. So in the wider machine learning and data science space, Python is really the dominant lingua franca, whereas embedded has C, maybe C++ as the languages. So how can we enable people that have machine learning skills already to build TinyML solutions in a way that they don't have to become firmware and C experts? So there's a project called MicroPython, which has been around for almost 10 years already, implements a subset of Python 3 for devices that have at least 16 kilobytes of RAM. And if you spend more than $1, if you spend $3, you get really powerful microcontrollers these days. So there's a lot of those. And it tries to stay as compatible with CPython as it can, it's reasonable. But it doesn't have C, FFI, or C module capability. So you won't have NumPy, scikit-learn, TensorFlow, or these kind of things. But it has a package manager, and you can install C modules at runtime, which I think is a super cool feature. And so the emlearn MicroPython project or sub-project is providing MicroPython bindings for this emlearn core library. And the goal is to combine the convenience, familiarity, and productivity of Python with the speed of C for these TinyML applications. So the modules it provides are installable at runtime, so you really have that Python development experience, even if you're working with a microcontroller board. You can just MIP install it. And we provide several machine learning models along with a few feature pre-processing tools such as IRR filters and FFT, because we saw that that was also lacking a bit in the microcontroller space. We haven't done a lot of benchmarking, but we could quickly see that it is at least 5 to 20x faster than plain Python. So there are some tools that can generate Python code, which you can put in MicroPython, and it works, but it's much slower and larger. And to use emlearn with MicroPython, on the host side is the same in terms of training, compile, and exporting. You just specify that you want it modeled in a CSV file. You can copy the CSV file to your device. So the MicroPython devices typically have a virtual file system, which is super convenient. You can store files. And then you download the emlearn library for MicroPython. So it's specific per model. And you need to have the right architecture, but you just choose the right one. And you copy it over to the device, and you're basically done with install, which is amazing from an embedded point of view. And it saves people from having to set up a C toolchain and SDK, compiling, building custom firmware, which, if you know it, it's a bit tedious. If you don't know it, it's almost impossible the first time. So this really is an easier way to do it. You load the model by constructing it with the desired capacity, put in the kind of weights or the model definition, and then you can predict on the input data. So the goal here is that, the hope here is that this will be useful for experienced developers, because you can prototype and even make production grade firmware with MicroPython, and you can use the productivity gains from Python and testability and so on. And you can mix and match as much as you want with C code. And then for people that are new to this area, new to TinyML, I think this can be a very accessible way of getting started. So in summary, emlearn is an open source project that implements primarily classical machine learning models for embedded systems. And I also talked a bit about tree-based models, which are very useful in a range of TinyML applications. And emlearn has a good optimized implementation specifically for microcontrollers and embedded systems. And by using MicroPython in combination with emlearn, it's now becoming feasible to build TinyML applications using only Python. And we hope this will have a good impact going forward. There's more information on the emlearn website, and of course I'll be around later in the break for any discussions, questions, projects, whatever you have it. Thank you.